everyone. Welcome to episode 15 in the Op-Amp tutorial series, Op-Amp Finite Bandwidth Part 2 of 3, Stability. In Part 1, we went over the typical features of the real open-loop gain transfer function of op-amps by taking away the infinite bandwidth and infinite gain approximations, then showed some loop gain transfer functions with some standard resistive feedback networks, and showed how those loop gain transfer functions translate into closed-loop transfer function plots, discussing the trade-off between frequency and gain in an op-amp. Today we're going to introduce the concept of feedback stability, demonstrate instability with an op-amp simulated in LT-Spice, then introduce the concepts of phase margin and gain margin, and how to use Bode plots of loop gain to evaluate the stability of op-amp circuits. So, feedback stability. The field of stability in feedback loops can get very mathematical. I'm going to do my best to avoid going deep into the math because I think the pure math is not really all that useful for most op-amp applications. That isn't to say that there aren't any reasonable situations where you might run into this issue, it's just uncommon. You are more likely to run into stranger stability issues in the field of power electronics. For the more simple op-amp feedback circuits that only contain passives in the feedback loop and do not involve transformers, you don't really have to worry about the weirder aspects of feedback stability. So for today, we will assume the loop gain of the systems we're using only contain poles and zeros in the left half of the complex plane. So, what is instability? Instability is when a system experiences positive feedback resulting in the output going to its maximum or minimum value, or, more commonly, oscillating at one or more frequencies. Recall from episode 13, when we introduced the general feedback structure, we specifically noted that we configured the system to be in negative feedback, not positive feedback. However, the transfer functions we're dealing with have phase shifts, and a phase shift of 180 degrees results in an inversion of the signal, which can change nice, stable negative feedback into positive feedback. Let's illustrate this with an example. Here we have the 808618 op-amp we used in Part 1. Now, the 808618 has an input bias current of around 1 picoamp, and thus we can use high input resistances and have very little effect on the output offset. So let's say we want a gain of 2 amplification and want to minimize power consumption. So we decided to use these two 200 kiloohm resistors to set the gain. I have a 10 microamp current source, which ensures that the op-amp is sourcing current regardless of its output offset voltage. This is a much better way to ensure that the top output transistor is active in the output stage, because it will have a much lower impact on the DC gain and dominant pole frequency than the 1K resistor I used to do this in the previous episode. Now notice I've put a 0.5 picofarad capacitor at the inverting input to ground. This is a rather small capacitance, and it is equivalent to a 0.5 centimeter long PCB trace that is 7 mils wide, routed 5 mils above a ground plane, that is, a ground plane on the second layer of the PCB if this trace is on the top layer. So not an unreasonable parasitic capacitance to ground for the conductor connecting the divider output to the inverting input. Now let's say that the output needs to drive a long cable, which, as a result, has a high capacitance, represented by this 200 picofarad load. This is the approximate capacitance of an 8-foot RG58 BNC cable. According to the driving capacitive loads portion of the 808618 datasheet, the op-amp can drive up to 500 picofarads without oscillating. However, it warns that external compensation is highly recommended for large capacitive loads and positive unity gain. We're not at positive unity gain, but we're pretty close, only a gain of 2. So it seems like we're okay to drive this 200 picofarad cable load, but the datasheet hints that this setup is tenuous at best. Now let's look at the step response, what the output looks like when I provide a sharp 0 volts to 100 millivolt voltage step on the input. The op-amp oscillates forever. The system is unstable. Note that while it starts oscillating with the step response here, this is due to the limitations of simulations. In a real-world circuit, there would be plenty of noise in the system to start the oscillation, so as soon as the circuit were powered up, it would oscillate like this. It seems like we adhered to the datasheet and used reasonable values. After all, 200K is a bit on the high side, but still a fairly often used component value. So what happened? To answer this question, we have to look at this circuit's loop gain, as that is the best transfer function to assess stability of the closed-loop system. Let's take a look at the loop gain of this op-amp circuit versus the loop gain of the same circuit without the capacitors. Here in black is the loop gain of the circuit without the capacitors, and in blue the loop gain with the capacitors. We see at low frequencies, the two curves have the same gain and phase. However, looking at higher frequencies, we see a very significant change in the phase and even the gain as new poles come into play. When the gain of the transfer function without capacitors hits unity, or 0 dB, the phase shift is around negative 98.86 degrees, far away from negative 180 degrees. However, when the gain of the transfer function with capacitors hits 0 dB, the phase shift is around negative 185.9 degrees. Because the phase shift is more negative than negative 180 degrees when the amplifier stops truly amplifying, we see oscillation in the output. This is how we use our Bode plot to determine if a system is unstable. A system is unstable if the loop gain's phase shift is less than negative 180 degrees. That is, more negative than negative 180 degrees, at the loop gain's magnitude of 0 dB, also called its gain crossover point. This makes intuitive sense, since a 180 degree phase shifted waveform with positive gain implies positive feedback. But running the risk of confusing the issue, that intuition is not exactly perfect, which is why there's so much math involved in feedback systems. If the loop gain's phase shift is less than negative 180 degrees when the gain is above 0 dB, but the phase shift recovers to greater than negative 180 degrees due to one or more zeros before the loop gain magnitude decreases to 0 dB, then the system will be stable. It is a concept called conditional stability, and it's not very intuitive since there will be a frequency at which a full 180 degree phase shift is occurring with greater than unity gain, yet the system works just fine, even when the input is a sine wave at that precise frequency. I will probably make a separate video outside this tutorial series about conditional stability, but that topic is beyond the scope of this series. Conditional stability is much more common in power systems, but a lot less common in simple op-amp signal feedback systems, so we will not discuss it any further in this video. So, back to the loop gain plot. The reason the circuit became unstable was because of two poles added to the loop gain. One pole was due to the small parasitic capacitance at the inverting input combined with the large feedback resistance. This is a common problem in op-amp circuits. The parasitic capacitance of the op-amp inputs and the PCB traces can cause a lot of trouble if you don't account for them. This problem is most prevalent in op-amps with high unity gain bandwidth, as even lower resistances will cause problems. That's why high-speed op-amp configurations tend to use much smaller resistances. It's also important to note that often simulation models will not model them properly. For example, according to the 808618 datasheet, there is much greater than 0.5 picofarads of capacitance on its inputs, but this SPICE model has zero input capacitance. I tested it to be sure, and it does not have a realistic input capacitance on its inverting input in this circuit. This is not uncommon, and yet another thing to keep in mind when relying upon simulation data. The other pole is due to the finite output resistance of op-amps, a non-ideality we have not yet covered, but is crucial to understand when driving capacitive loads with op-amps. The finite output resistance of the op-amp creates a pole with the 200 picofarad cable load capacitance. This adds a pole to the loop gain. The result is that prior to gain crossover, the phase shift due to the poles internal to the op-amp, as well as these two new poles, is more negative than negative 180 degrees, and the system becomes unstable. So, all we need to make the system stable is to make sure the gain crosses the 0 dB point prior to the negative 180 degree phase shift. A simple way to do that for this system is to just decrease the divider's resistances. Setting those resistors to 49.9K each, we have the same closed-loop gain. And now, at gain crossover, the phase hits around negative 169.6 degrees, more positive than negative 180 degrees. So everything's now nice and stable. That's all we have to do, right? Well, let's look at the step response of the system now. The input voltage is in red, the output voltage of the op-amp circuit with capacitors is in blue, and the output voltage of the op-amp circuit without capacitors is in black. The circuit with the capacitors is ringing a lot from this step, And the version without capacitors has no ringing at all and looks very close to what the input looks like, gained up by a factor of 2. So while the system is now stable, it's not exactly working out nicely. It's actually doing two undesirable things here. First, it is overshooting, which is when the output voltage exceeds the expected gained up value. This circuit is supposed to gain the input up by a factor of 2, so it should be outputting 200 millivolts, but instead it's outputting over 1.75 times that value, to almost 360 millivolts before coming back down and settling to 200 millivolts. This can be a huge problem if the op-amp is connected to a circuit that will exhibit nonlinear characteristics if it sees too large of a voltage. The second thing that's bad is its ringing, which could be a big problem, especially if the downstream electronics are like a comparator and sensing a threshold. The ringing op-amp may go above and below that threshold, triggering the comparator to switch states multiple times when it should only do so once. This ringing and overshoot is caused by the phase shift in the feedback, just like the instability was. In this case, the oscillation does die out, so the system is stable, but it is an extremely undesirable effect. These effects show up as peaking in the closed-loop transfer function. Here's a plot of the closed-loop transfer function in the frequency domain. The black trace is the closed-loop gain of the circuit without capacitors, and the blue trace is the closed-loop gain of the circuit with capacitors. In the underdamped circuit, the gain magnitude rises significantly right before it starts falling off. This is the peaking that produces the ringing. It's due to a double pole in the closed-loop transfer function that has a low damping coefficient, which is why it rings in a similar way to what you would expect from an underdamped LC circuit. So, how do we fix this? By minimizing the phase shift at the loop gain's gain crossover frequency and minimizing the gain at the point at which the phase shift becomes negative 180 degrees. Looking back at the loop gain plot, the phase at gain crossover plus 180 degrees is called the phase margin, and negative 1 times the gain in dB at phase crossover is called the gain margin. It's negative 1 times the value in dB so that the value is positive for stable systems. The bigger these values are, the less ringing and overshoot the system will experience. Intuitively, the reason for this is that the further the system is from negative 180 degree phase shift at gain crossover, the less positive feedback is introduced into the system, and similarly, the lower the gain, below unity, the system is when the phase shift finally does hit negative 180 degrees, the less positive feedback is introduced into the system as well. The lower the phase and gain margins, the more the circuit will overshoot in response to a step function, or ring. So our system had a lot of ringing in it because the phase margin was very low, but even more modest phase margins, like 25 degrees or 30 degrees, will have a significant overshoot. A general rule of thumb is for a system to have adequate phase margin, it should be at least 45 degrees, with 60 degrees or more being good phase margin. A phase margin of around 90 degrees is even better, but is usually unnecessary, and since it requires that there be no more than one active pole, it is difficult to accomplish. A good gain margin is around 10 dB or more. People generally focus less on gain margin because if you have a good phase margin, an adequate gain margin will follow in most situations. For the op-amp circuit without the parasitic capacitances that cause the instability, the phase margin is 81.14 degrees, and for the circuit with the capacitances after the fix we implemented, the phase margin is only 10.38 degrees. The gain margins for these two circuits are 19.53 dB and 2.69 dB for the without capacitors and with capacitors versions, respectively. So we can see that the version without capacitors has very high gain and phase margins, making it robustly stable and without any ringing. The version with capacitors has very low phase and gain margins, making it ring a lot. So now that we understand that phase and gain margin are the parameters we need to adjust to make the system work more smoothly, we just have to tweak those parameters. Stabilizing feedback loops and improving the phase and gain margin for a given circuit is a complicated process that is heavily determined by the requirements of the circuit and the op-amp in question. For some situations it is easier, and in some situations it is extremely difficult or even impossible, especially if strict constraints are placed on the amount of power, cost, and size of the solution. This process is called compensation, or compensating the feedback loop, and it is the subject of the next video in this series. That concludes this episode. In this episode, we talked about how to use Bode plots of loop gain to assess stability of a closed loop system, showed an example of instability with an op-amp and LT-Spice, introduced the concept of phase margin and gain margin, and demonstrated the effect of phase margin and gain margin on ringing and overshoot for the closed-loop op-amp step response. In the final video on the op-amp finite gain and bandwidth arc, we will discuss the concept of feedback compensation and how to improve phase and gain margin by using some external compensation methods. Thank you for watching the video. If you enjoyed it, please like, share, and subscribe. If you have a question or comment, please leave a comment. See you next time.